Okay, welcome to section 1.3, where we're going to now look at the integral of a function, one type of integral of a function. In section 1.2, we looked at estimating the derivative, and we found that the derivative was when we looked at the slope between 2 points, and as we brought the second point closer and closer to the first, we could estimate the derivative or the slope of the line at 1 point on the graph. This was called the instantaneous rate of change, or the slope of the tangent line. And this was rise over run, or the change of y over the change of x. And when we talk about rate of change, we're talking about units of the y-axis divided by the units of the x-axis. For example, if y is distance in miles and x is time in hours, our derivative becomes miles per hour. In this section, we are going to look at something called an integral. And you have worked with simple integrals in the past. Let's look again at a very simple graph where, for example, we have velocity on the y-axis, or something like miles per hour, and then we have time on the x-axis, for example, hours. And if I told you that we were going 60 miles per hour for a period of 3 hours, you would tell me that we had traveled a 180 miles. Now, this is a simple distance equals rate times time problem, where distance is 60 miles per hour times 3 hours. And our units changes to miles, and we get 180 miles. So the integral of the graph is actually the area under the curve. When we have a straight line and a straight line, you can see that this is the area of a rectangle, or 3 times 60, and the integral is 180. So that works great when we're talking about a constant rate of speed, a constant of 60 miles per hour. But when we are talking about calculus, we're talking about curves, and you will see that the integral will allow us to find the area under a curve. And let's again use our hours and miles per hour. When, however, the rate of change, or the velocity, is not a constant. So how do we find the area under this curve when the y values are not a consistent value? This is called the definite integral. The definite integral evaluates the product of two variables when one factor varies. In this case, it was our y, or our velocity. There are two ways to calculate the definite integral of a function. One is to look at the graph. And what we're going to do in this section is we are simply going to count squares on a piece of graph paper to find the approximate area. If you think back to when we did derivatives or slopes, we found the approximate slope first, and then we brought it down until we could find the actual instantaneous rate of change. The other way to evaluate a definite integral is to do so algebraically. We won't be looking at that until chapter 5, so you're just going to have to wait for it. So let's look at this definite integral. If you will pause the video at this point and look at example 1 in your textbook, you can see that they are using a sheet of graph paper and simply counting squares. Please take a moment to look at example 1 in your text. If you'll flip the page now and look at example 2, they're going to be doing the exact same thing, counting squares under a curve. Obviously, you'll be using graph paper for this section, and you will be using a graph, and you're looking for just an approximate value, doesn't have to be exact, and we're looking for the area under the curve. So here's our definition for our definite integral. For any function f of x, remember that's your y value, the definite integral of the function from x equals a to x equals b gives us a way to find the product of b minus a and f of x, even if f of x is not a constant. And this is what we are looking at here. If we are going from point A to point B, and we want to find the area under the curve from A to B, or this distance, which would be b minus a, and we want to find the area under the curve of f of x. If f of x is a constant, we just have to multiply, like in my first example where our constant was 60 miles per hour. But if f of x is not a constant, we need to use a definite integral. And at the moment, our method for doing definite integrals will be counting squares or partial squares on a sheet of graph paper. So good luck at this time. Please do your homework for section 1.3. You will be doing the Q questions, numbers 1 through 10. These questions are very important. They shouldn't take you more than 10 minutes to do all 10 of them. They are a quick review to keep us focused on what you should already know. If any of them are difficult for you, come back and look at them after you've done the regular homework and see if you can find out. And then you'll be doing 1 through 11 odd, and I would like you to do 12 through 14 all problems. Please make sure you are using graph paper so that you can be as accurate as possible. This is an estimate that we are dealing with, but we want to be as accurate as we can. Thanks so much. Good luck.